Hi all and welcome to Six Sigma and Processi Produttivi YouTube video channel. This tutorial is about normality of data. If you remember my second tutorial in English, we were talking about the normal distribution, how to build a normal distribution, the shape of the normal distribution, and we were talking about real-life distributions that follow the normal distribution, the shape of the Gaussian curve. Some examples were the people height in a given geographical region, or the dimensional values of injection molded parts, or the example of the tutorial that is the number of M&Ms in M&M's bags. This tutorial will give us a scientific method, a statistical method to understand without to have a clear statement about the normality of data, because in tutorial number 2, when talking about the examples of M&Ms, we counted the number of M&Ms in a set of 20 bags. Each number was represented with a cross in a Cartesian axis diagram. We plot all of the crosses, they were 20 crosses, and at the end the layout, the shape of the histogram given by the crosses did remind us very strongly the shape of the normal distribution, the shape of the Gaussian curve. But that was simply a let's say a graphical analysis, just an idea that they could follow the normal distribution, because the distribution of crosses did remind the bell shape of the Gaussian curve. But is really existing a scientific method, a statistical method that provides us evidence that the data, real set of data follow the normal distribution? Yes, there is, and this is what we will see in the present tutorial. Minitab helps us in doing this, and you can see here Minitab. Just clicking on the Minitab 20 icon, you will get this image, and I prepared for you some data, exactly the data presented in tutorial number 2. If you remember, in tutorial number 2, we were talking about 20 bags, each bag containing a given number of M&Ms, and these were the numbers reported. There were 6 bags with 28 M&Ms, 5 bags with 27 M&Ms, 4 bags with 29 M&Ms, and so on. It's important, and it's written here, to know the statistical index that provides us the evidence that a real set of data follow the normal distribution. It's the p-value. If the p-value provided as an output by Minitab is more than 0.05, we can say with 95% confidence that the data follow the normal distribution. And we will see how to obtain this p-value presenting two statistical methods that Minitab provides us to analyze normality of data. I put also in column C1 the 20 data. I can show you that they are 20 data. We can see 6 values of 28 as it is also summarized here. Then we have 5 values of 27 as it is outlined here, and so on. So we have the 20 data, exactly the same 20 data of M&Ms in bags that were presented in tutorial number 2. But if in tutorial number 2 we stated, just basing on a graphical analysis, just basing on the histogram shape of crosses, that they were following the normal distribution, now we want to provide the same evidence with a statistical tool, with a statistical evidence. How to do this? Well, just click on Stat, Basic Statistic, and we have 2 methods, the graphical summary and the normality test. I prefer the graphical summary, and we will see why. If you double click on graphical summary, there is this window where in the field variables you have to click to select the column of your data. So it's column C1 where we have M&M's data. This field by variables, as it's written here, it's optional, so we can leave it blank, and then Minitab assigns by default a 95% confidence level. That means that if we will make a decision on normality, we will have 95% confidence on this decision. We can click OK, and we have this graph. The reason why I prefer this method is that the graphical summary graph as an output of this analysis provides us the same histogram we obtained in tutorial number 2. In tutorial number 2 we got this histogram by putting the crosses on a Cartesian axis, and here we have the same histogram that reminds us immediately the shape of a normal distribution, as you can see by the red Gaussian curve here. So just visually, this graph tells us that these data are normal, but the real value is here, the p-value, which is 0.196. That is pretty higher than the value of 0.05, which is the threshold. So being 0.196 more than 0.05, it means that the data with a 95% confidence follow the normal distribution. We have additional data as the mean, which is 27.8. This is a value that has not much interest, since we were dealing with 20 whole numbers, 20 integers, so providing a mean of 27.8 with one decimal is not so useful, because the number of M&Ms in a bag can be 27, 28, 29, but not decimal numbers. The same for standard deviation. Then we have the variance, which is the standard deviation square value, and then we have the n number, which is the number of values analyzed, that was 20. So the data followed the normal distribution. So we confirmed the output of the graphical analysis performed in tutorial number 2. But we were talking of an additional method. Let's see what it is. Let's go to Stat, Basic Statistic. Instead of performing graphical summary, we can perform also normality test. Before going here, let's have a look at the fact that here it's written Anderson-Darling normality test. So just clicking on Stat, Basic Statistic, Graphical Summary, we are performing the normality test called Anderson-Darling. If we go to the other method, Stat, Basic Statistic, Normality Test, double click here, and we have this window where we have to select the column of data to analyze, which is again column C1. there is a predefined selected option here by Minitab for test for normality, which is Anderson-Darling. So clicking OK, we are just repeating the same test as before, so we expect to obtain the same p-value. Just click OK, we get this graph that we can magnify a little bit, and we see that we got the same p-value 0.196 as before, so the data are confirmed to be normally distributed, and this was obvious because we were analyzing with the same method, Anderson-Darling, the same set of data. We have the same mean, we have the same standard deviation, we have the same number of values. How to interpret this graph? We have a straight line, more the red dots reside close to the straight line, more the data follow the normal distribution. Every dot, of course, every blue dot, of course, represents the value, one of the value of the values of the 20 set of data analyzed. The data are close to the straight line, but there can be scenarios where the data follow shape like this one or like this one, so very far from the straight line. In this case, we would obtain non-normal data. Okay, so it's very easy. I want to show you an additional example. Minitab can give you the choice to generate normal data, and I will generate for you a set of 20 normal data. Just go to Calc, Random Data, Normal. We can generate 20 data to store in column C2 with a mean of 20 and a standard deviation of 1. Just click OK. We have 20 data here that I can call with the name of the column D1. These are 20 data normal, because generated normal by Minitab. So let's analyze them just for confirmation of the p-value with stat basic statistic graphical summary. I select column C2, same confidence level. We can leave this field blank, click OK, and we have obtained this graph. Okay, for D1, the same graphical summary that provides us also for us this beautiful histogram. The value is 0.503, but pretty higher than 0.05. So the data are tremendously normal. We have a mean of almost 20, and this was expected since we generated 20 data with a mean of 20. The standard deviation is approximately 1, and this was expected since we generated 20 data with a standard deviation of 1. And then we have the number of values generated, which is 20. So everything is normal, and the data follow the normal distribution. But let's figure out that these data are 20-dimensional data, 20 diameters of 20 round-shaped parts coming from an injection molding department, measured by an operator with a very precise instrument, let's say visual profile that provides us a high number of decimals. So in this case, up to 4 decimals after the integer number. And let's figure out that we take the same 20 parts and we measure them again. We measure them again, the diameters, but with a very less precise instruments that provides us with no decimals. Okay, so let's call this column D2, where we put the same 20 data, but rounding them to the whole number. So the first value becomes 21, the second value becomes 19, the third value becomes 20, and then I will fill up all of the other cells accordingly. So we have here 19, then 21, then 18, 20, 20, 18, 20, 18, 21, 20, 20, 20, 22, 21, 20, 20, 18. It's obvious that the differences that were clear and evident in column D1 are not so evident in column D2. The differences between the numbers have dramatically decreased. So, for example, we can see two values like this, where 20.6, 20.4, so very close values that became very different, 121 and 120. So there is not a difference of one between these two numbers, but of course, rounding them up to the integer numbers, we can magnify or reduce the real differences. Okay, so let's analyze again this 20 data rounded with the same method. So go to Stat, Basic Statistic, Graphical Summary, select D2, 95% confidence, leave this field blank, and click OK. We get this value, this graph related to column D2. We have again the histogram that reminds, of course, the shape of a Gaussian curve, but the p-value is below the threshold of 0.05. It's 10 times lower, so it's 0.006. What happened? Well, the effect of rounding, the effect of using not so precise instrument is in fact losing normality. Don't beat me up wrong. Data are still normal. Data follow the normal distribution, but they lost their normality because of using the wrong instrument. Okay, so if you remember my introduction video, of course, the purpose of this webinar is to learn some statistical tools, is to learn how to use the statistical tools to understand the data of our production process. Why? Because we want to detect immediately if there are deviations in our processes, if there is something that is going wrong, if there are signals or triggers. If you remember, we were using exactly these terms to be alerted and to work on the process to solve problems, which is behind the data. In this case, let's figure out an operator that every day goes into the production process, into the injection molding process, takes 20 shaped parts. He measures every day 20 parts with the visual profile instrument and put the data in Minitab. He performs the normality test. He gets a value of higher than 0.05 and everything is fine. Okay, every day the production is under control, the process is under control, but one day he takes 20 measurements, he inserts the data in Minitab, he performs the normality test, and the data turn out to be not normal. So what happened? Okay, we don't know. We have a trigger in Minitab, so the p-value, which usually is higher than 0.05, that turns to be less than 0.05. Okay, we don't know what happened, but we know that something happened. We know that there is a problem, that something drove the process out of its normal behavior. There could be different scenarios. It could be that in the injection molding department that day the operator working on the injection molding machine were using the wrong parameters, or it was used the wrong raw material. It It can be that the operator wasn't well that day and he took wrong measurements, or as in this case, he was using the wrong instrument. In this case, making this example, we immediately came to the conclusion that the origin, the cause of the problem was the use of the wrong instrument. But the importance of using these tools is to immediately provide a trigger, a signal that must be analyzed because it is the symptom of something in the process that was going wrong. So the power of these tools, of these statistical tools, is very high, and we will see other examples using other statistical tools that will be presented in the next tutorials. Why is normality of data important? Normality of data is important because there are other very powerful statistical tools such as process capability, CPK, PPK indexes, such as ANOVA, such as t-test, that can be performed only if the data to be analyzed follow the normal distribution. They can be used also if the data don't follow the normal distribution, but if they don't follow the normal distribution, they have to be performed in a different way, using different methods, using Minitab in a different way, selecting some options instead of other ones. So it's very important, because performing an analysis of data with statistical tools, thinking that the data are normal while they're not, this could lead to very wrong results, and we would be forced to act on the process when in fact it is a wrong approach, because probably the problem doesn't exist. So normality of data is very important in view of applying other very powerful statistical tools that we will see in the next tutorials in Minitab. Well, this tutorial is finished. Thank you for staying with me. I hope that you enjoyed this tutorial. If you liked it, please put a like in YouTube. Please subscribe if you haven't subscribed yet, but I want to thank you because now we reached to 227 subscribers, so I'm very happy for this. There will be upcoming English tutorials about CPK and PPK, so please stay with me, because the next tutorials will be very interesting and with a lot of application in real world operations in many companies, in many factories. Thank you all again. See you at the next tutorial. Bye bye.